Okay, so as we said in that slide 14, we begin with our booklet knowledge, if you want, that the redshift can be calculated as the change in the wavelength over the emitted wavelength, or that redshift can also be calculated as the value of the scale factor at present time over the value of the scale factor some time ago minus 1. Remember this value here, the scale factor the scale factor at present time and the scale factor before tells you how much the universe has stretched, so that carries information about obviously how much those waves have stretched. Well, this can be further backed up if you take these two equations. I'm gonna just take this one first, the one with the wavelengths, and I'm gonna say that, well, that delta lambda over lambda 0 is equal to lambda over lambda 0 over lambda 0, which is equal to lambda over lambda 0 minus 1 if you just divide here by lambda 0 each one of the terms. So what you get is that, well, lambda over lambda 0 minus 1 equals r over r 0 minus 1, which, no surprise, leads to lambda over lambda 0 is equal to r over r0. Now, what are all those things? Well, you need to remember lambda is the observed wavelength currently, or in the present, and then this lambda 0 is the originally emitted wavelength. Okay, so let me just write the word wavelength. Okay, so r then would be the present value of the scale factor of r, and r0 I'm gonna say value of r when lambda 0 was emitted. So in comparing lambda and lambda 0, we're getting an idea of how much the universe has expanded from the moment when it was originally emitted, that radiation, to present times. And that, according to our little derivation here, is or has this exact same ratio as the value of the scale factor back then when the wave was emitted to the ratio of that with the scale factor at present time. So the ratio of present wavelength up here to emitted wavelength down here is equal to the ratio of scale factor when it was emitted, scale factor, present value of the scale factor over value of the scale factor when the wave was emitted. And this gives you an interpretation of the scale factor where you can see that it's actually a number that measures the size of the universe. Basically, it's not the size itself, but it's related to the size of the universe. And then by analyzing both the value of the scale factor before, when that radiation was emitted, and the value of the scale factor now, you can get an idea of how much the universe has expanded. Okay, so that's what we are at this point. So the whole point is that we're also trying to connect this. So let me go back to that. Up to this point, we have connected the redshift that we observe from galaxies, which is this factor here. We have connected it with the evolution of the scale factor since then to present times, which is this factor over here. Now, that connection is very important because it gives you a different interpretation of the origin of the redshift. Now, we said that the redshift is observed because galaxies are moving away from us at a velocity, and so we apply Doppler effect to that velocity, and we can obviously detect the redshift. But this equation here actually gives you a different interpretation because the wavelength change between the emitted and the observed is actually not coming from the galaxies moving away from us, but it's coming from the universe itself increasing its size well as we speak. So this scale factor is what we use to give a cosmological explanation to the redshift. And that's why slide number 14, at the beginning, you can read cosmological redshift. So it's not the usual redshift that is produced by just a velocity. If you remember the analogy of the balloon that is increasing its volume, when I was drawing those dots on the surface of the globe that I have here in the classroom, the points were not moving on the surface of the globe, but it was the globe itself that it was increasing its size. So is a slightly different interpretation. So that's why I'm saying this result here. I don't know what figure that is. I was going to draw an arrow. So this equation here actually offers a completely different view of why that wavelength is increasing, and this interpretation has to do with the scale of the universe. Now, we also said that the universe from the beginning has been emitting radiation as every object with a temperature would do, and that radiation led us to calculate the average temperature of the universe looking at the wavelength of the cosmic microwave background. And we did that by using Wien's law. If you remember, from the booklet, let me see, where is it? From the booklet, I lost it, yeah. From the booklet, what you get is that maximum wavelength of emission times the temperature is equal to a constant, right? That constant in the booklet is 2.9 times 10 to the negative 3 meters times Kelvin. But the point is that that is constant, and that was constant before, and that is constant now. So actually, if you look at the wavelength that was originally emitted times the temperature when that wavelength was emitted, that should be equal to the wavelength at present times the temperature that we get at present times. So the ratio of lambda over lambda 0 from this equation can be written as T0 over T. What you need to remember is that, well, this T is the temperature of the universe when lambda 0 was emitted, right? And this T here is the temperature at present time, right? So we're getting to something like interesting here because we're starting to connect not only the that redshift with the scale factor of the universe, which gives us that cosmological interpretation, but also we're connecting it to the temperature of the universe. So if we take this equation that we just obtained here and we compare it with this one that we had up here, then what we would observe is that T0 over T, whoa, what was that? T0 over T is equal to R over R0. Now, the implication of this is simple, and it's the fact that T0 times R0 is equal to T times R. Now, if that's the case, then that means that the product of the temperature of the universe times the scale factor back then is equal to the temperature at present days times the scale factor at present days, which is a very important thing because that is telling you that at any time in the history of the universe, T times R has remained constant, right? And if T times R has remained constant, that means that T is equal to a constant over the scale factor, which means that, well, T is actually proportional to the inverse of the scale factor. And that shouldn't be surprising because what this implies is that when the universe was very hot, then it was very small. And when the universe cools, then it gets bigger, right? And I can say that because I can see that the temperature is inversely proportional to the scale factor of the universe. And remember, the scale factor talks about size. So as the scale factor increases, that means as the universe increases its size, then the temperature goes down. And as the scale factor decreases, that means back in time when the universe was way smaller, the temperature gets higher. So up to this point, we had been saying like, well, yeah, the universe is like a big ball of gas, and as every gas, if it expands, it cools down. But that's a very simplistic interpretation. That's very, very simplified in terms of everything that we should take into account. And this equation here that we're obtaining actually gives us a more a better interpretation of why the temperature of the universe is decreasing as the universe expands, and it's connected to things like the redshift, the scale factor, Wien's law. So it's not a simplistic interpretation where we say just the universe is a mass of gas, which we know it kind of is, but it's much more complex than that. And it's taking into account many of the cosmological variables that we've been studying. So this equation here is actually a very good thing to obtain because it's giving us using the cosmological variables that we've studied is giving us evidence that actually the universe is getting cooler as it expands.